Greetings, folks. We're starting to deal with simple harmonic motion, and this video is going to talk a little bit about amplitude of oscillatory motion, and when we're dealing with spring systems, ideal spring systems, spring constants. Okay, so the amplitude of an oscillating body is the magnitude of its maximum displacement from equilibrium. So some examples: body attached to a spring, sitting at equilibrium. The system is pulled out to some maximum displacement. It's allowed to oscillate back and forth. The maximum displacement is the amplitude. Same system. In this case, the spring is initially compressed, the body is released, the system oscillates back and forth. The magnitude, the maximum displacement, once again, is the amplitude. Here we have a mass spring system hanging in the vertical. Body is pulled from equilibrium down to some maximum displacement and released, so it oscillates back and forth. Maximum displacement, once again, the amplitude. And here's the same system, except initially the spring is compressed from equilibrium, released, allowed to oscillate back and forth. Maximum displacement is the amplitude. So not to beat a dead horse, the amplitude, it's the magnitude of the maximum displacement from equilibrium. So we're going to be working with ideal springs that essentially follow Hooke's law. Hooke's law says that the force that's required to displace a spring is proportional to the displacement of the spring. The proportionality constant is called the spring constant, and the spring constant effectively measures the amount of force per unit distance required to displace the spring from equilibrium. It's effectively measuring how stiff the spring is. Mathematically, it's equal to the magnitude of F over the magnitude of X, where F is the amount of force that's required to displace the spring from equilibrium at distance x. So here is the body at equilibrium. You displace it at distance x. So here's the displacement. The force that's required to hold the body in this position is F. You take the ratio of that force to that displacement, it gives you the spring constant. Units are newtons per meter. So here are your homework problems. You have a spring that's sitting here in equilibrium. It can either be compressed or elongated. You attach a mass to it, and you elongate the spring to this position right here. If it took 12 newtons to get the mass to hold at this position right here, what's the spring constant? For part B, we assume that the body is then released so that it can oscillate back and forth. The question is, what's the amplitude of the motion? Question number 2, you've got a spring that's hanging. Again, it can be compressed or elongated. You attach a mass to it, and you slowly allow the mass to elongate down to this position here. The mass is a ½ kilogram. Once it gets to here, it just sits. You want to know what the spring constant is. Once you get done with part A, you take the mass and you push it up to the 60 centimeter mark and release it so that it begins to oscillate up and down. What's the amplitude of the oscillation? Okay, so brand new situation, brand new spring. You put the ½ kilogram mass on it, you elongate it some distance or compress it some distance, you get it oscillating, and you find that the frequency is 4/10 of a cycle per second. And you'd like to know what the spring constant is. Okay? This is a problem that if we've gotten far enough in class, you should be able to do. If we haven't, it's something that you ought to look out for. And if you can't do it, don't worry about it. But if you can, finish it off. Anyway, that's it.